welcome everyone to this webinar. And today we're going to talk about secure boot and firmware updates. And we start with a short introduction about the purpose of the project and the solution that we offer for secure boot and firmware updates. So when we talk about IoT security, we know that there are about 30 billion of IoT connected devices nowadays, and more adding to internet connections every second. And we wonder, how did IoT security improved lately? So is security, as in the joke, still the S in the IoT acronym, or have we improved the way we perceive and we implement security in those systems? We should be able nowadays to identify what are the security threats specific to internet connected devices, but we should always ensure that we implement what is recommended by the standards, as we do for other larger systems. And we have to be sure that we understand how vulnerability management works, and specifically for these small systems. What we recommend is to always keep into account vulnerability management on any kind of connected systems. We have to use the best technologies up to the latest standards. WolfSSL was the first commercial vendor on the market offering a TLS 1.3 support, which is described by the IETF, the International Engineering Task Force, as the most important security protocol update since the beginning of SSL connectivity. But this is sometimes not just enough, because once we release a product with everything up to the latest and greatest standards, we must ensure that we keep everything updated, because there might be vulnerabilities that are discovered later on after we release our product to the market. And on a microcontroller system especially, this is a very important threat, because it means that a small vulnerability in one part of the system can potentially compromise the entire system. That's because of how microcontroller system has a flat memory based architecture. So this is very important, especially on smaller devices. And so even if we implement the latest standards, we always need a way to update what we have deployed on the field. And that's why nowadays secure remote updates have become a security requirement for all these connected devices. From the point of view of threat analysis, there are many possible attacks that an attacker can try to perform on our devices. So it can try to they can try to run unauthorized firmware on the target. So if we have a weak or no authentication at all of the current running firmware, this might be a problem, because an attacker could use our firmware update mechanism to inject a malware into our devices. Or, for instance, they can try and extract the data from our devices, or try to escalate some vulnerabilities in the code to inject some malware or other kind of malicious code inside the device. And finally, of course, reverse engineering is also a threat, and to circumvent our IP protection. And this is also done sometimes with false injection, or even more expensive attacks like done with IC the cap and SEM techniques. So with this in mind, we try to find the best way to implement secure firmware updates and secure boot as recommended by IETF, because we do always follow the best standards available. And what we found is that there is a research group within IETF that's called SUIT, that is a group that currently research on the specific topic of the updates, of secure updates and secure boot for IoT devices. And they still in the draft phase, but they already do have standard requirements for how a secure boot and secure update system should look like. And we started from these requirements when we decided to implement our own solution for this. So some of these requirements are the fact that the bootloader itself should be agnostic on how firmware images are distributed. And should, for this reason, allow also technique of the broadcast delivery, for instance, to many devices at the same time. It should use state-of-the-art security mechanisms, which means that it needs to use standard algorithms for cryptography, for instance, to verify the authentication of a firmware that's being transferred. And it should prevent rollback attacks. So, for instance, trying to reinstate the previous version of the same firmware that has been validated, but it is obsolete and might contain vulnerabilities that are already known and fixed in newer versions. We must have high reliability. We will see what this means. And the bootloader must be small in size. And this is not just a requirement due to the restriction of the limited amount of resources available on systems, but it is also because typically a lot of bugs that could allow an attacker to escalate and counter the current security mechanisms in place are because the parsers are too big and may have bugs. So the smaller the parser, the less the possibility of introducing bugs while parsing the information that is stored along with the firmware image, like for instance the metadata in the manifest header of a secure firmware update. And among other stuff, other requirements, the bootloader has to provide a secure mechanism which is based on asymmetric cryptography. So this includes those algorithms that are based on a key pair, so a pair of public key and private key that are more robust when for the goals and the purposes of authenticating a firmware update, or in general the firmware or all the software that has to run on the microcontroller or on the embedded system that we target. What is the approach that many IoT companies take nowadays is to build their own secure bootloader. But building your own secure bootloader might seem like a smaller part of your development, while in fact it is a complex project. You shouldn't be relying on the fact that it has a small size, because it is often easy to underestimate the effort, especially on the testing of the corner cases, or having a good testing mechanism for code safety and everything that's related to key management, how to create and handle the keys and use them to sign the firmware. And so this is often an issue for the costs that are hidden in this kind of challenge, especially it's going to impact on the time to market and other phases of your project. So would you write your own TLS library or TCP/IP stack or real-time OS from scratch for your own project? It feels a bit like reinventing the wheel, right? So it goes the same for a bootloader. That's why we started a few years ago the development of a universal secure bootloader that could be portable across multiple types of system, that uses state-of-the-art security and cryptography mechanisms, and it is based on a public key as recommended by the standard, and has a small footprint and a lot of safety measurements, such as the exclusion of dynamic memory use and or using any interrupt at boot time. And in fact, this is also providing a reliable firmware update mechanism, which is independent from the transport mechanism as mandated by SUT. And it can also do fallback to a previous version, let's say a golden version, when the update fails. So that's how Wolfboot was born. Wolfboot is our open source universal secure bootloader brought to you by WolfSSL, and it is designed for the IoT systems. It follows the requirements as we mentioned, and runs on most 32-bit microcontrollers. It was initially written for ARM Cortex-M microcontrollers, and later on we had a port thanks to the RISC-V Foundation, a port to the RISC-V RD32 devices, and later on we have integrated it also on more complex systems like 64-bit ARM CPUs, even with multiple cores, and where on ARM-V8 architecture we can make use of trust execution environments such as TrustZone, which is part of the safety critical architecture of those systems. And the bootloader is OS agnostic in the sense that it can be integrated with any project, being bare metal or based on a real-time OS, and even provides support for booting more complex kernels that are massive memories, such as Linux. And it can be integrated in an existing chain of trust, so it can run at different boot stages, and it does firmware authentication every time the device boots. So every time that your target will boot, it will the bootloader will check for the authenticity and the integrity of the firmware before running it. And it even has some very unique features in the market, such as the support for secure elements and crypto hardware accelerators, which comes from the cryptographic support from Wolfscript, which is compatible with the drivers provided by many manufacturers to access those secure elements. And it also supports TPM 2.0 devices. This is done through the WolfTPM library that we offer in order to communicate with these TPM devices, which is a standard to communicate to external secure elements that are coupled with the microcontroller or the CPU in the system. We recently added support for encrypted storage, so it is possible to send an encrypted update to the device, and this will be stored encrypted, and then during the installation, the bootloader will use a symmetric key, in this case, to transfer the update from the update partition to the boot partition, and vice versa. It will store a backup of the current working image encrypted in in the secondary update partition. Wolfboot is also capable of updating itself. In some cases, when the public key is embedded in the code of the bootloader, this is the only way to provide an actual key revocation in case your private key is no longer valid on your server side and you want to change the public key. The bootloader can receive a bundle to update itself. We provide portable tools for key management, both in Portable C and in Python, and that allow you to sign and manage the keys for signing your remote updates and the firmware. And of course, it is actively maintained by our excellent worldwide team of engineers, and we always work on full-time on new features, bug fixes, improvements, and we do offer support packages up until 24/7 support for our premium customers. And it is highly portable, as we said. It's not just agnostic of the OS being used, but also on the platform, because the platform-specific code is limited to just a few routines. So just the hardware abstraction layer, as we call it, is very minimal. It consists usually of just a few functions to access the specific Flash driver implementation. And all the code, as all our products, is available on GitHub with a GPL v2 license. This is how a secure system should look like. On the right-hand side, you will see your normal firmware running your application or your real-time OS with security libraries, probably Wolfxl, running with Wolfscript and the TCP/IP stack, and also network drivers and other drivers that are provided maybe by the manufacturer. What Wolfboot expects is that you integrate a small library that's called libwolfboot, which consists of just a few calls to interact with the bootloader that you can see in this picture on the left-hand side. Wolfboot relies on Wolfscript for the public-private key authentication. There is a public key trust anchor, which in the most basic case is embedded inside the code of the bootloader. The public key is not secret and can be just buried into the code of the bootloader. And then it uses the Flash driver, the part in orange, that's specific for the architecture. Everything else is generic code provided by default. How does the key management work? The key pair is usually generated once, and the private key is stored on the server, and it's never shared. That's your secret, basically. While the public key can be stored on the target, there are different ways to do this. What we require is generally a trust anchor, as defined by IETF, and then this sign tool that's portable, written in C or Python, that attaches this manifest header, which is used as metadata to validate the integrity and authenticity of the image, because it contains the signature and shard, digest, etc. The firmware version is also part of this verified payload. So the firmware version cannot be altered without compromising the integrity and the authenticity, which means that Wolfboot can rely on the version as well to avoid rollback attacks, as described earlier. So Wolfboot can rely on a trust anchor to embed the public key used for the signature. In the most basic case, the trust anchor is just the signature that's stored and cannot be modified by any external source, and it is constant. For instance, write protected part of the Flash itself. This is the definition of trust anchor given by the IETF, and sorry, and the suit requirement is just that the trust anchor for a secure boot must resist against modification, because this is the immutable part of the entire process that guarantees that all the firmwares can be validated against the private key that lives on your server, on your backend, or a developer machine, and it's never shared or put inside the device. This is how the key management works. Very briefly, you create a key pair and then embed the public key inside Wolfboot. And then if you have your own firmware and you add the version number, for instance, version 2, you can, through the tool, generate a signed firmware using the private key. And this firmware on server then can be authenticated by Wolfboot after the transfer, and then Wolfboot will allow you to run it on the device. Update management can work in two ways. Very briefly, you can have an A/B approach, so two partitions that are equivalent, and you have to, and the bootloader can choose which one has the newest firmware, contains the newest firmware, and of course, after verifying that, it will just run into it. But on most microcontrollers where there is no virtual memory possibilities, at that point, we use a boot update approach. So the two partitions are different in the sense that the active firmware is always running from the boot partition, and the update partition is only used to receive the updates. And this is the default in all systems, like microcontroller based, where you cannot do any virtual memory mapping, and all the mapping is relies on the physical address of the two partitions. So the A/B approach is more complicated, especially from the point of view of the deploying the firmware and sending the updates. That's why we do implement both in Wolfboot, but for most cases, we recommend the boot update approach. In the boot update approach, we have one small partition between 10 and 32 kilobytes that contains the bootloader, and that's at the beginning of the flash executing space, and that has, of course, hard-coded address. One boot partition, that's the one that contains the firmware that we decide to boot at that point. The update partition will receive new updates, and there is a little swap partition that is used as temporary storage when swapping the content of the two partitions, the boot and update partitions. So update to swap partition can also be mapped on external non-volatile memories such as SPI flash, and as we said, they can be encrypted using a symmetric key that is as a temporary value and can be set through the libwolfboot. So as we said, there is a possibility to roll back in case something goes wrong after the update, even if the firmware is validated. There must still be containing a bug. So if the update is not confirmed, the bootloader at the next reboot will perform a rollback, which ensures that your device can still work properly if the update failed because of a bug or a human error on the field. And that gives us the best reliability available for secure boot solutions on the market, because we always store a backup copy of the other firmware, of the older firmware, in the update partition during the update installation. For what concerns application endpoint, so it is very easy to integrate Wolfboot in an existing project. You just have to move basically the beginning of the firmware in the linker script of your application, so that it takes into account the fact that there is a bootloader at the beginning of your flash memory. This is a bit how the manifest header looks like. It contains a lot of useful information, and it's normally 256 or 512 bytes that's prepended to the attached to the firmware image, so that it contains all the information and the signature that the bootloader can use to verify the image, but also contains other important information such as the version or the timestamp when the image itself has been compiled. So in a real-life scenario, what we do is just we have factory firmware that we can transfer to a JTAG, and this includes the bootloader, of course, and your first factory firmware. So this is version number 1. It is the firmware that is deployed during the production of the device. So from this point on, you can disable your JTAG or just put bright protection in place so that you're sure that an attacker with physical access to the device cannot overwrite any of the parts of your internal flash. In this case, we're talking about the internal flash, but as said, the update partition and swap space can be elsewhere, such as an SPI flash or an external device in general. So you have, more in general, when your device is deployed on the field, you have a current firmware and an empty update partition. So when you implement, at every boot, Webboot will verify that the firmware is genuine and it's authentic, and then if everything goes well, it will boot the current firmware version, right? But then, when you want to transfer a firmware update over the air, for instance, you have to do the process of signing it using our tools, and then transferring to the device the firmware update that contains the signature, and this can be stored on the update partition. And this is done usually internally by your application that's running in the current firmware, which is aware that can store the firmware update there. So at the next reboot, the bootloader will verify the update, and if the update is genuine and authentic, it will swap the two images. So now the new firmware update is contained in the boot partition, and so if the verification is successful, so we can install the version 2 of this firmware. But the previous firmware is kept as a backup in the backup partition. So this means that if something goes wrong and you can't confirm that the firmware is running properly, the bootloader at the next reboot will swap it again, and then the old firmware can be restored, and this is done with the same swap operation, but in the reverse direction. But otherwise, from the next boot up, the new firmware becomes a current firmware, and the update partition is empty again, and it is ready to receive the next firmware update. Lastly, we have a default Logixl, which allows us to always have the behavior of the bootloader under control. So at every boot, we check if there is an available update, and if it is authentic, and in that case, and it's also newer than what we are running now, and in that case, we begin an update. While if no update is available, we just verify the authenticity of the current running firmware, and then we can stage it, so run the actual firmware on the device. The swap operations are interruptible. It means that they are fail-safe. So the power can be interrupted at any time, even on the worst possible point, which means that even if there is a power failure during the update, the bootloader is capable of resuming that operation as soon as it gets boot again. And yes, there are many ways to perform secure firmware updates. We do have a recommendation based on the products that we offer that are all standard products. But of course, as we said, the bootloader itself is agnostic on the way that we transfer the image. So it is possible to integrate with your current solution. This concludes the the presentation for now for me. So I'd like to address some questions if there are any. I see that there are already a few questions asked offline. One concerns the protection against fault injections attacks. We do have some workaround for fault injections attacks, but unfortunately, those that are typically addressing a specific hardware model that contains some vulnerabilities might be difficult to tackle in a software environment only. So in those cases, when you care about fault injections attacks, we recommend that you use an external hardware device, such as a key vault or a TPM, to prevent that. There are mechanisms to prevent any fault injections attacks, such as voltage glitching or EMI glitching, and other types of attack that target the hardware itself. And I see there are other questions. Yeah, one was specific on the NRF52, which reports voltage glitch attack. In that case, it can be the NRF52 can be used can be coupled with an external hardware security module or TPM device that will prevent the attack to happen. And about ARM's recommendation secure boot specification, there are some activities done by ARM on the standardization of secure boot and secure firmware updates, but I'm aware that some of these efforts has been brought towards the SUT group, which is the official standardization group for these topics, and it's exactly where we started from, and the requirements that we follow come from the IETF draft from the SUT group, which is currently on the draft number 8, but we expect that will be standardized soon.